Good afternoon.
Good afternoon.
All right, let's see. So who's missing in Moyan?
Just Rachel.
Rachel. She's one of those choir kids, huh? Let's see. How about in St. John's? Oh, there's everybody, right?
Yep.
And then are we missing Chloe today?
No, we were in a class meeting.
Oh,
She's
okay.
here.
Okay, thank you.
Mr. Strong, did you get my email about this week? Here. So we have.
Oh, soccer, right?
Yeah.
Yeah.
We could be gone from like either just Wednesday or from Wednesday to Saturday.
Okay.
So.
All right. Well, we'll just so if you miss, so Wednesday, I think what we have planned is the chapter 3 test.
Okay. Could I take that tomorrow?
So yeah. What time? Or do you
I
want
would say 10:50 to 11:50.
Okay. Oh, so that's okay. So what the plan is for us is that because we want to get I want to get the midterm done. Okay. So even though we will have not taken quizzes on the last couple of sections, I want to go ahead and do the chapter 3 test this week because we're gonna finish chapter 3 today. So then you can have till Wednesday to do the chapter 3 test, and then we'll do the midterm next week. Okay. Now it might seem a little early to think about this about next week. But we actually, I'm going to give you the, so we might, during like testing time or whatever next week, we might, do quizzes or whatever we need to do. But really what I'm thinking about for the midterm is we'll do that during class time. Okay. So it'll be during class time next week. And so it's so the midterm is in 2 parts. And so it's going to take up 2 days of class. So my question is do you want to do it like Tuesday and Wednesday of next week, or like Wednesday and Thursday of next week? Does anyone have a preference as far as the 2 days for the midterm? Again, we're not talking this week. This week we're going to do the chapter 3 test. So it's next week that I'm thinking about. So do you guys have any druthers?
Wednesday and Thursday for me.
Yeah, I agree with that.
Okay.
Yes.
Everybody
I
okay
don't-
then?
Yeah, Mobian said Wednesday, Thursday.
All right. So let's plan on that then next week. And so we'll talk more about it as we get closer to it. I'll give you the breakdown. So we'll plan on Wednesday and Thursday of next week. Okay, so I'll start kind of working toward that. All right, let's see. All right, so we have a little bit to do here still left on chapter 3. So 3.9, we're talking about the differential. So let's see, where's that? Okay. So we are at
Mr. Strong?
4. Yes.
I'm sorry. Since we're finishing chapter 3 today, does that mean that the rest of the days are going to be review, or are we going into chapter 4?
We'll be going into chapter 4.
Okay.
Okay. So, yeah, so because I need, the reason why we're doing that is because theoretically, I would love to have the midterm done this week, but I don't want to do the midterm before you've had a chance to have the test on chapter 3. So, you kind of bone up for chapter 3, then focus on, reviewing. But having said that, while I do plan on going on to new material, what I would actually hope is as you're reviewing for the midterm, I will allow, especially next week, like Monday and Tuesday of next week, I'll sort of budget some time at the beginning of class where if you want me to review something or if you have a question that you've attempted to do and you're not getting the right answer, from the practice problems or whatever, I would be happy to go back over anything from the first 3 chapters. So we can kind of do some review, but we kind of need to keep moving, especially if I'm going to miss two lectures next week. Okay. All right. Anything else before we get started for today? One other thing is, so tomorrow, because we are going to finish chapter 3, I am going to send out the student success organizers for chapter 4. So be on the lookout for those in the morning. Okay. So that you can get those printed off. All right. Well, let's go ahead and get started with this. Okay. So where we are here is on 3.9, linearization and differential. So we kind of finished the linearization, and I talked a little bit about the theory of relativity. And now we're going to go to differential. So we're in part 4 on the front side. Okay. So what is the differential? Well, a differential is how we use derivatives for approximations, basically. If you want to know how something is changing approximately, instead of doing a lot of calculations that would, maybe require a calculator or something, a differential is a way that maybe with some simple calculations, not having to use a calculator, you could approximate. So back in the day where calculators weren't so accessible, the idea of a differential to use as an approximation, that would be like a big deal. If you could do simple math from with a little bit of calculus, it would make the problem a lot easier. So how we do it is, if you think of the derivative, y prime, we can write it as dy dx. And so it's kind of a weird idea that, where we think of the change in y with respect to x. But if we solve this for y, it's kind of like, it's a little bit of an abuse of notation here, where you think of multiplying each side by dx as if it were a number. And so you get dy is the derivative times dx. Okay? So the differential dy is the derivative times dx. So that's really the only new math step here, is you still go about taking the derivative, is now you're just going to solve for dy by multiplying each side by dx. Okay? So let's say we had y equals 3x squared. Well, if we write the derivative dy dx as 6x and just multiply each side by dx, you'd get dy is 6x dx. And so that's the differential. The dy is the differential, and it's just, what it means is it's an approximate change in y. Okay? An approximate change in y. All right? Now, suppose that we are told that in addition to our function, let's say we want to find dy for this function, and we're given a specific value for x and a specific value for dx. All right? Well, let's go through this. So dy dx, you just take the derivative, 5x to the fourth plus 37. Then multiply each side by dx. So this has to be in parentheses here. Okay? All right, then if you're given a specific value for x and dx, then you just, after you've solved for dy, just plug in the given value for x and the value for dx, and then work it out. Then it just becomes a calculator thing, or you just crank it out. So 0.84. So what does that mean? That means that for this function, at this value for x, if x changes just 2/100ths, then y is going to change 84/100ths. So y is way more sensitive to change here than x. Okay? So it just is an approximate change. Okay? All right. So go ahead and do practice 4, please.
Wait, Mr. Strong, I have a question.
All right.
Is this kind of like the epsilon delta a little bit?
Kind of, because you're saying that is, I guess the epsilon, x is changing this much, then how much would y have to change? So it's kind of like that idea. But yeah, you're splitting the dy dx, the derivative, into the different parts, the change in y's and the change in x's. So yeah. All right, so Hammond Z, what's dy? Right.
dy equals 4.4.
Okay. That's it. So you take the derivative, and so dy is the derivative times dx. Then you plug in 2 for x, 0.1 for dx, and so then when you crank it out, you get 4.4. All right, great job. Any questions on that? All right, so finding differentials of functions. So in place of dy equals f prime x dx, we can write df, which is the differential of the function. Now, this df, I really don't care for this notation very much. So you won't see that very often on quizzes or tests, but the book uses it, and so so the df dx, or just the df, that means the same thing as dy, and then they usually give you the function there. Okay, but it just means the same thing. So if I say d and then the function, okay, that's like saying what's dy. So you take the derivative of that times dx, okay? So that's what that means, d and then the function, okay? So it's the same thing as saying y equals tan 2x, find dy. See, I like that better. To me, that's a little more clear. So if I wanted to take the tangent of 2x, the derivative of tangent is secant squared. So the derivative of tangent 2x is secant squared 2x. And then remember the chain rule. You have to multiply by the derivative of 2x, which is 2, and then times dx. And so that's your differential. And so you could clean that up by putting the 2 in front, but that's about it. That's the answer. All right, we're looking at another one. So if I say d and then a function, then that means find the dy. So it's the derivative times dx. So in this case, I would need to use the quotient rule. So I start with the denominator, x plus 1, times the derivative of the numerator, which is 1, minus the numerator, x, times the derivative of the denominator, which is 1, all over the denominator squared, times dx. So the dx is multiplied by everything. And so now if I clean that up in the numerator, I get x plus 1 minus x. So the x's cancel. And so I just get 1 times dx, or dx over x plus 1 squared. All right, so go ahead and try practice 5, please. All right, so David, what do you have for A?
Okay, so I kind of got the derivative of that equation, but I don't remember what to do after that.
Okay, so what's the derivative of secant?
Is it tangent?
No, it's not tangent.
No, it's
Secant.
secant times tangent. Yeah.
Secant tangent.
Okay.
So then what's the derivative of secant 3x?
Secant 3x tangent 3x times 3.
Yes. And so the new thing that we're doing today is you're just multiplying by dx. Okay? So it's just secant 3x, tangent 3x times 3 times dx. Okay? So the only new step today is just multiplying by the dx. Because we're splitting dy dx, and then you can put the 3 in front if you want. But the only new thing today is for the derivative dy dx, we're multiplying each side by dx. All right, Hannah Z, what do you have for the second one? Or when you get it.
Negative x cosecant x cotangent x plus cosecant x plus times dx.
Okay, so negative x, cosecant x, cotangent x, plus cosecant x, and then it's all times dx. So make sure you put a parentheses around that or something, because you don't want the dx just multiplied by the last thing you said. It's all multiplied by the dx. Okay, great job. Any questions on that? Anyone like me to go through it? Okay. All right. Okay, next, estimating with differentials. If we know the value of a differentiable function x, f of x, at a point, and want to predict how this value will change if we move to a nearby point, a plus dx, if dx is small, then dy is approximately equal to delta y. So dy is the differential that we've just been calculating. The delta y is what we're talking about, the exact change. So to compute the dy, okay, this is the calculus that we're doing. Calculus. Okay? The exact change, the delta y, that's algebra.
How do you know if dx is small? What constitutes small?
that's the age-old question for calculus. It's kind of like, how close can you get? Well, as close as you want it to be. So I mean, I guess relatively speaking, usually it's within like, a tenth, 2/10, something small, less than 10% of what the value is. But it's kind of a arbitrary question. What is small? Well, it's just a little bit more than where you are. But it's a great question. But in calculus, there really is no answer to that. Okay. So, okay. So let's say that here we have a radius changing from 10 to 10.1 inches and of a circle. And we're going to use differentials to approximate the change in the area. Okay? Now, so if we're going from 10 to 10.1, then we're saying that difference is small because we're going from 10 inches to 10.1 inches. So it's not a huge change. It's not like we're going from 10 inches to 100 inches or something like that. Okay? So we're going to say that R is 10 and the dr is how much the radius is changing. So if we're going from 10 to 10.1, the dr is 0.1. All right, so we think about our formula for the area. So area is pi r squared. And so then if we take the derivative of that, so we're saying that dA, the approximate change in area, is 2 pi r dr. And so then we plug in 10 for r and 0.1 for dr, and so we get 2 pi as an approximation. Now, I want you to think for a second, to get this answer of 2 pi, how hard was this math? Not very. Okay? We did all that in our head. 10 times 0.1, 10 times a tenth, it cancel. We just ended up with 2 pi. Okay? So the approximation using calculus is actually easier if you understand the calculus. Because, see, now let's do the exact change. So the exact change in area, if the radius is 10.1 minus the area if the radius is 10. So that's 10 times 10.1 squared minus, or pi times 10.1 squared minus pi times 10 squared. So what's that? See, I can't, that's 100 pi, I guess. Anyway, my point is that this, we almost have to use a calculator for. Okay? And so if I calculate this, put this in the calculator, I get 6.315. Okay? Is the actual change in area in square units. So square inches. Okay? So this is the exact, the actual change. This is the DA, the approximate change in area. Okay? So now, if we want to know what our error is, and a lot of the things in this section, they talk about different ways to calculate error. Okay? So the error is, well, if you take the exact change minus the approximate change, the error in our estimation here, the actual minus the differential, is 0.031. Then to calculate the percent change, if you take the error divided by the actual, the error divided by the actual times 100, then here's the error, 0.031. The actual was 6.315. The error divided by the actual is 0.005. And if we multiply that by 100, that's 0.5%. So the error in using the calculus, which is way easier, without a calculator, we were only 0.5% off, which is not bad. Okay? So again, 100 years ago, say, that, as mathematicians would do these calculations like in their head, they would do stuff like this. And they could do it quickly and easily, and just the average person that didn't understand calculus were so amazed that they could be so close. And usually their computations weren't even scrutinized that closely. Is that they could quickly do an approximation using the differentials. Okay. All right. So we're going to talk a little bit more about the error in this. Okay. So I'm going to leave this up on the board. I want you to do practice 6, and I apologize for the lack of space for that one. I guess you're going to have to do it somewhere else. But go ahead and try. So here we've got the radius of a sphere, not a circle. Increases from 10 meters to 10.2 meters. Use dV to estimate the approximate percent error. So I want you to go through all of this, find the actual change in volume, use the differential to find the approximate change in volume, and then calculate the percent error. So see if you can do all of that. All right, David, what's the formula for the volume of a sphere?
No.
Say it again, please.
Oh, the volume.
The volume of a sphere. What's the formula?
Over 3 pi.
Okay, I'm only hearing like half of it, and you're getting muted in the middle of your answer. So say it one more time.
4 over pi cubed?
No, it's not 4 over pi. It's 4/3 pi r cubed. Okay. All right, so Skylar, what is dV?
4 pi r squared times dr.
Excellent. Okay. All right, next. I want to know what is dV when r is 10 and dr is 0.2. right, Skylar again.
251.327.
Okay, great. All right, any questions so far? So that is the approximation. And see, this calculation really wasn't all that bad. I mean, especially if you left it in terms of pi. Okay. You could have done that in your head. Now, to do this, you'd probably use a calculator. But 251.327 cubic meters. That's the approximate change in volume. Okay. All right, now, to do the actual change in volume, you don't use the calculus. You go back to the original problem, calculate the volume at 10.2 R, at R of 10.2, and an R of 10, and then subtract. So that's will be the actual change in volume. All right, so Hannah Z, when you've got that.
1.97%.
Oh, okay. So the delta V is 256.387. And so then the percent error is you take you calculate the error between those two, and then it's the error divided by the actual times 100, so 1.97%. Okay, so you're right on. I actually wasn't asking for all that, but kudos to you. You did it all. All right.
Could you scroll up just a little bit, please?
Yeah, sure. So the part in blue, that's the actual change in volume. Okay? So that's the no calculus required. You just plug in 10.2 into the formula, plug in 10 in the formula, and then subtract. And then you subtract those answers, and that gives you the error. How far off you were. What the heck is going on there?
Oh, sorry.
Oh. Sounds like you guys are starting Halloween early in Winslow.
Oh, yeah.
All right. Can I go on?
Yes, thank you.
Okay.
Can you stay there for another minute?
Sure. All right. You got it, Jordan?
Yeah, I'm good. Thank you.
You bet. All right. All right. So let's look at this one. This is practice 7. And I just want to use the differentials and we'll kind of work through this together. So if you think of you're wanting to do the sine of pi 6 plus 0.01. So think of this as your x and this is your dx. Okay. Well, so the sine of a plus dx is the sine of a plus the cosine of a times dx. Okay? So this is what goes in the blank there above this problem, this part in red. It's like the formula that you're using. So to plug this in here, you're going to say, okay, this is the sine of a. So the sine of pi 6 plus the cosine of pi 6 times the dx, which is 0.01. Now, at this point, because you can, you could get an exact value here and here, but then when you multiply it by 0.01, you could put it over 100 if you wanted. I would just say at this point, just put that whole thing in your calculator. So the sine of pi 6, make sure you're in radian mode, plus the cosine of pi 6 times 0.01, the dx. And then you'll get the decimal approximation 0.5087. But see this 1/2, and this one's radical 3 over 2, which would be radical 3 over 200. You could actually get a fraction without using the calculator. But so this is kind of a cool way to do some of the harder trig values that you used to not be able to do before calculators without using differentials. Okay. All right. So sensitivity to change. So as we move from A to a nearby point, A plus dx, we can describe the change in f in 3 ways. Okay? So the actual change, now what I've written here in red is kind of how I would write it on the paper if I were taking notes. So the absolute change is the change in the y. So the delta y, the y2 minus the y1, the change in the y values. And so then the relative change is the change in y's over this y2, the second y value. And then the percent change is you take that answer times 100. So all of that, this is just the algebra where you're doing the exact values. It's when you're doing the estimated, that's where you're using the calculus. And so this is the differential that we learned today. The dy is the derivative times dx. And then the second one, the relative change, is the dy over the y value, the second y value. And then the third one is you take that times 100, the last answer times 100, and that gives you your percent change. So when you read through this section, they do a lot more about percent error and so on, and I'm not doing any of that. There's other formulas and stuff. I'm just focusing like on what we did on practice 6 to do the percent error. Okay, so practice 8 says you want to calculate the depth of a canyon from the equation S equals 16t squared by timing how long it takes a rock you drop to hit the bottom. How sensitive will your calculations be to a 10th second error in measuring if the rock hits at 3 seconds and at 6 seconds? So what this is talking about is you can use the sound to estimate the depth of a canyon, of a rock, or a well, whatever. And so the question is that if you're just a 10th off in timing how long it takes your rock to hit, how far off could your calculations be? All right? So if you start with your S, so S equals 16t squared. So ds would be 32t dt. So at 3 seconds, you plug in 3 for t, and then the time, you're a 10th of a second off. So the ds is how far off you could be in your depth of estimate. Okay? So see if you can do part B for tomorrow.